Anyway, just picking up with the next item and continuing on with functions, and we've looked at in various capacities what are referred to as quadratic functions. Since we've been working with the quadratic equation and solving through various techniques like the zero product property, the square root property of equality, as well as the quadratic formula. And we have, in the case of quadratic functions, okay, and we have just as a definition for quadratic function, and there is a form or a display for the quadratic function that we're going to be looking into. And okay, now for a quadratic function, okay, this is going to be by definition, okay, you're going to have a second order function. Okay, and there are two forms we're going to be looking into. Okay, and the first, okay, we have the standard form. It's going to be, okay, and we're going to have that y is equal to f of x and we have is equal to ax squared plus bx plus c. Okay, and just again emphasizing, okay, the second order part. Okay, this is going to be in reference to the highest degree term in the function. Okay, so we're looking at second degree in the independent variable, which we have in this case to be x. Okay, and so this is going to be the standard form. Okay, and there's another form we're going to be looking at, and that is going to be what is referred to as the vertex form. Okay, so we have for the vertex form of a quadratic function, okay, and we're going to sort of rearrange the terms that we have from the standard form. And there's going to be a bit of a change up in terms of the variables. Okay, now for the vertex form of a quadratic function, okay, we're going to have that y is equal to f of x. Okay, and we're still going to maintain the use of a, but now for the components we have with the rest of the variables like b and c, we're going to have different letters to be on display, and we'll have a times, and we're going to have in parentheses x minus h, and this is going to be to the second, and we have followed by the letter k. And we're going to have some translations between the standard and the vertex forms of a quadratic equation. Now, regarding this display of the quadratic function, some things about the letter a. Okay, if the value is positive, okay, if a is positive, okay, now you're going to have the graph of the function it's going to open upward, okay, from the vertex. And the vertex is going to be a particular point, and the coordinates will be with the letters h and k. So here, like your x value is at h, your y value is going to be at k. And for what we have with the leading coefficient, okay, so if we have that a is negative, Okay, now you're going to have the graph to open down from the vertex. Same point, or at least in terms of the general format. Okay, and just some of the features we have regarding quadratic function. Okay, and we have sort of a dividing line that's going to separate the graph of a quadratic function, and you're going to have what is referred to as the axis of symmetry. And the axis of symmetry, okay, this is going to be like a visual vertical line. That's going to divide the graph into equal halves that are going to mirror each other. Okay, and okay, now regarding the term vertex. Again, we have the coordinates at HK. And for what we have here, okay, this is going to be the location from which the graph of the quadratic equation opens. And for what we have in the case of a quadratic function, okay, now the graph of a quadratic function is going to be a parabola. And it's going to be something that's like a mix between what looks like a letter U and a letter V if you're looking at opening upward. Okay, I just put up a couple of cases here. Now, the other week we had terms like relative minimum, relative maximum, and you're going to have the vertex to be either a relative minimum or a relative maximum, so to speak. And so we have just in the sort of the samples here. Okay, so we have just as a case of parabola, okay, and we'll just say one whereupon the graph is going to open upward. I'm going to put both versions of the quadratic function case. So again, this is the standard. And again, we have the vertex form. And we have with the point from which the graph opens. Then we have HK. And again, just splitting the graph. Okay, so you have dividing up into equal mirroring halves. Okay, now both sides, okay, should be mirroring. The sides should be mirroring each other, and my sketch might not exactly represent that. But again, these two ends should be mirroring each other. And for what we have in this particular instance would be with the behavior of the graph. Okay, so we're going to have that A is positive. And we're talking about the very same letter A here. And so you have A is positive, so you have that A is greater than 0. And this signals that f of x is going to open up. And whenever the graph opens upward, okay, this means that for the vertex, notice you have HK is the bottommost point of the graph of this function. So you're going to have that the vertex is going to be regarded as the location of the minimum. Okay. All right. So this is a case of what we have with the quadratic function, okay, where the leading coefficient is positive and where the graph is thus going to open up. Okay. Now, for what we have, let's say that if you have a situation where you have a bit of the opposite motion. So we have the point HK to be on the top. And before I get too far ahead, okay, this red line here, x equals h, okay, that is going to be what is referred to as the axis of symmetry. Likewise here, okay, so you have x equal to h. Okay, so we have axis of symmetry. Okay, and once again, we have with our function, again, so you have f of x equal to ax squared plus bx plus c is equal to a times the quantity of x minus h squared followed by k. And this time around, you want to have that a is negative. If it's negative, okay, so it's going to be less than 0. Okay, and this time f of x opens down. And for what we have in the case of the vertex, okay, that is going to be the maximum. Okay, and okay, so this is the layout. Okay, so a quadratic function can be expressed in terms of the standard form as well as the vertex form. And now between the forms, okay, now the first section, chapter 2, stresses the vertex form, but if I were working with word problems, especially like with vertical motion and all that, I have a tendency to gravitate more toward the standard form. I guess it all depends upon what you get used to. And but now just still for what we have on the vertex form, and just kind of give you a little bit of a case here where we have specific values for H and K. And let's say that just taking what we have, for instance, okay, so we can say that we have given f of x and say we have x minus 2 squared plus 5 and say we're looking for 3 components here. Okay, see we have first of all, okay, say the direction, that the graph of the function is going to open. So for what we're going to have here, okay, so you have, again, just for the vertex form, okay, so we've got f of x is equal to, and again we have a times the quantity of x minus h raised to the second, followed by k. Now for this particular function, okay, so again we have f of x, okay, and we have is equal to x minus 2 squared plus 5, okay, and for what we have in this case, okay, so you don't have anything explicitly in front of the binomial, okay, so this a is going to be 1, okay, so you have a is equal to 1, and 1 is a positive number. So that means that for what we have in consequence, okay, we have the f of x is going to open upward. All right, now let's say we have second part here, okay, say we're looking for the axis of symmetry. I'll just copy this portion here. Going back to our equation. Okay, so we have with the numbers here. So you got the vertex form, and then we have, again, we have the quadratic function. Again, so a is at 1. And now for the h value, okay, we're not using the zero product property, but you can think along the lines of like what would be the zero of x minus h, and that's going to be your h value. Okay, and so for what we have here, okay, so you have with x minus 2, I'll just kind of give you a case here. So you have with x minus h is equal to 0, and if x minus h is equal to 0, we have the x is equal to h. So that would be your axis of symmetry. in the general case. Now we have with x minus 2 representing x minus h. We have x minus 2 is equal to 0, and we have that x is equal to 2. And so for the axis of symmetry, I'm just going to say AOS, shorthand for axis of symmetry. So axis of symmetry, okay, so that is going to be at x is equal to 2. And in the case of the identifying the vertex, okay, so we have in the case of the vertex, okay, so you have so again, just from earlier, like what we have with the axis of symmetry, let me do it this way. Okay, so we got x minus 2 is equal to 0, x is equal to 2. And again, just taking from the page, okay, just for the general representation of the vertex or the axis of symmetry. Okay, so you have x is equal to h. So we have the x is equal to h is equal to 2. And for what we have in the case of the k value, we have that k is equal to 5. So we're going to have for the vertex, okay, so you got h and k. So h is at 2, k is at 5. So we have with the ordered pair, okay, we end up at 2, 5. Okay. Okay, so we're going to use y in place of f of x. You have y is equal to x minus 2 squared followed by the addition of 5. Okay. So we get this to show up as well. Okay, and if you notice, okay, we have we got the graph of y is equal to the square of x minus 2 plus 5. Okay, and now for again the vertex, okay, that's going to be located at 2, 5. So that is going to be the minimum in this case. So that's going to be the vertex, and the graph is going to open upward. And again, this blue line here, okay, that is going to be the axis of symmetry. And we can say that just for the layout, okay. And we'll say that we have let's see. There we go. And we'll say that we have f of x is equal to negative 2 times, okay, we say we have the square of x plus 5, and we have minus 10. Okay, and let's say that if you were to identify, let's say the direction the graph opens up, and you're looking for the axis of symmetry as well as the vertex. Okay, so just kind of having gone through this round, okay, from the first example. Okay, so just kind of moving things along. Okay, so again, you have with the general layout of the vertex form of a quadratic function. Okay, so we already had the vertex form laid out for this particular function. Okay, so leading coefficient, okay, that is going to be at -2. Okay, so A is negative. So I'm signaling that A is less than 0. Okay, and so we're going to have that f of x is going to open downward. And for what we have in the case of the axis of symmetry, as well as the leading coordinate for the vertex. Okay, so we have with x plus 5, we have x plus 5 is equal to 0, and we have the x is equal to -5. And we're going to use this value in a couple of capacities here. Okay, so we got for the axis of symmetry. Okay, that is going to be at x is equal to -5. And we have with the value of k, okay, so we have that -10. So we have that k is equal to -10. And so we're going to have for the vertex, with the vertex hk, okay, so that is going to be at -5 and -10. All right, and so, okay, and again, just providing a bit of a visual. Okay, so you have -2 times the square of x plus 5. Then we have -10. Yeah, let's see, they might have to. Yeah. Ah, there we go. It's playing hide and go seek. Okay, so you're going to have the graph is going to be opening downward. Okay, and in case of the axis of symmetry, again, we had the x is equal to -5, so that line is in red. Okay, and again, just for the vertex. Okay, so again, the location is at -5, -10, and again, the graph is opening downward. And once again, the axis of symmetry, what x is set equal to is also going to be the h value in the vertex. Okay, so the axis of symmetry always passes through the vertex, and that is how from the vertex on upward or on downward, we're going to have the graph of the parabola to be divided up into equal mirroring halves. Direction that the graph opens, as well as the axis of symmetry and the vertex. Okay, so let's see what we get for the direction that the graph opens, the axis of symmetry, as well as the vertex. Okay, for the following two functions. Okay, and we'll say that we have f of x is equal to 3 times the square of x minus 7. And also with the other function, we'll say we have f of x is equal to -2 times, okay, the square of x plus 6 plus 25. Okay, so for the next few minutes, okay, let's see what direction the graphs will open, as well as their respective axis of symmetry, as well as the vertex. All right, for both of these functions, okay, they are already provided for convenience sake in the vertex form. Okay, so we have, for the first function, we have f of x is equal to 3 times, okay, the square of the binomial x minus 7. Okay, so just looking at what we have in the layout, okay, if you notice, okay, we have a corresponds to 3. So you have a is equal to 3, so a is going to be positive. And this will signal that f of x opens up from the vertex. For what we have in the case of the axis of symmetry, okay, so if I take the 0 of what represents x minus h, so I have x minus 7 is equal to 0. So I have that x is equal to 7. So we have for the axis of symmetry, we have x is going to be equal to 7. And we have in the case of that which represents k. Notice you don't have anything added or subtracted. And since there is a void, we have that k is equal to 0. Okay, so the graph opens up. The axis of symmetry we have at x is equal to 7. And for the vertex, that is going to belong on the x-axis where we have it 7, 0. Okay. And again, just to quickly illustrate, so you have the axis of symmetry at x is equal to 7. And again, for the vertex, we have on the x-axis at 7, 0, and that is the point from which the graph of the parabola representing y is equal to f of x is equal to 3 times the square of x minus 7. Okay, so this is, again, so this graph represents the opening parabola of this particular function. And for what we have in the case of the second function, okay, already provided in vertex form, and we have for this one, okay, so you have a is equal to negative 2. Okay, so you have the a is negative. So this signals that the graph of f of x is going to open downward. As for the h value, okay, we have that to be the 0 of that representing x minus h, which happens to be the addition statement x plus 6 which we set to 0, and so we have x is equal to -6. So again, we have for the axis of symmetry, we have x is equal to h is equal to -6, and now we have a k value. Since we have at least something added, in this case we have that k is equal to 25. And so we're going to have for the vertex HK. Okay, so that is going to be located at -6 and 25. So just looking at what we have here. Okay, so you have with the axis of symmetry. Okay, so you have x equal to -6. And again, the vertex is going to be the point from which the graph is going to open downward. And again, that location we had at -6 and 25. Okay, so again, this is going to be the vertex, and which is also going to be the maximum of this function. All right, and so these 3 items, okay, those are among the early stages, or I should say just among the introductory portions of what we have in the mechanics concerning the graph of a quadratic function. And let's say that just sort of expanding a little bit and venturing out a little further into some of the other portions that will define the graph of a quadratic function. And we'll say that we have and just kind of stressing the symmetry a little bit more as well. And let's say that if we have given f of x, okay, is equal to, okay, we say we have the square of x plus 4 minus 4 and we were to determine the following. Okay, so we have if we have the direction that f of x opens, the axis of symmetry, and again the vertex, and see we have the intercepts, the x-intercepts and the y-intercepts. We also have like the identification of at least 5 points. Okay, so just kind of referencing what we have once again. So for the first 3 components, okay, again, we had this function is already laid out in the vertex form. So you have with this function, okay, so we have in vertex form, and again, the void of a coefficient in front of the parentheses. This will signal that we have that the leading coefficient a is equal to 1. So that is going to be positive. Okay, so the graph opens up. And as for what we have for the h and the k values, so x plus 4 is equal to 0, so we have x is equal to -4. And for the axis of symmetry, again, we have x is equal to h is equal to -4. And for what we have regarding the k value, okay, since we have subtraction at the end, okay, so we're going to have that k is equal to -4. So you're going to have, for the vertex, so the vertex hk, so h is at -4, and so is k. All right. Now, okay, so you got the first three parts. Now where the intercepts are going to come in, okay, and a while back, okay, we looked at x and y intercepts. And again, for x-intercepts, you're looking at, in the function or the equation, you're looking at setting y equal to 0 and solving for x. And we have for the general coordinates of the x-intercept, okay, so you have x, 0. And now, for what we have for the function, again, we have y is equal to f of x is equal to the square of x plus 4 minus 4. And again, just stressing, okay, so that which represents y, in this case, we should have f of x, okay, we're just going to set this equal to 0. Okay, so have 0 is equal to the square of x plus 4 minus 4. And what we can do here is that we can sort of take from the page what's going to lead up to the square root property of equality. Okay, so I'm going to isolate the square of x plus 4, so I'm going to add 4 to both sides. So we have that 4 is equal to the square of x plus 4. And what I'm going to do here is I'm just going to switch the order, like going from b is equal to a is equal to b format. So we have the square of x plus 4 is equal to 4, and then following through with the square root property of equality. Okay, just going back, so you have for the square root property, x squared is equal to p. We have x equal to plus or minus, okay, the square root of p. So if I do the same thing here, so x is represented by the binomial x plus 4, so if I go from the second degree and that to just the first order, so yeah, plus or minus, okay, the square root of 4. So I got x plus 4. Now, square root of 4 is 2, and I'm going to have x plus 4 is equal to plus or minus 2. And looking at what we have upon separating. So you're going to have, at the lower end, we have x plus 4 is equal to -2. And at the upper, okay, we have the x plus 4 is equal to 2. And if I take 4 away from both sides, okay, so if x plus 4 is equal to negative 2, okay, so I have the x is equal to minus 6. And if I have the x plus 4 is equal to 2, taking 4 away from both sides, so I have the x is equal to negative 2. Okay, and so for what we're going to have in effect, okay, so for x equals negative 6 and x equals negative 2, that's one way upon which we can display the x-intercepts. And also we have in coordinate fashion, we have negative 6, 0, as well as negative 2, 0. And for the y-intercept, and for a lot of these problems with the vertex form, the y-intercept is probably going to be the easiest one to get to. And for what we have here, so you got, okay, so you have y is equal to f of x is equal to x plus 4 quantity squared minus 4. Again, so we're going to have x is going to be set to 0. So for what we're going to have in the case of y, so y is going to be f of 0 is equal to 0 plus 4 squared minus 4. So we got 4 squared is going to be 16. And we have 16 minus 4, which is going to be at 12. Okay, so we have a couple of x-intercepts, where we have x at negative 6 and x at negative 2. And we'll have one y-intercept at y is equal to 12. And in terms of coordinate fashion, we'll end up with the ordered pair 0, 12. All right, so in terms of the entire makeup, and again, just kind of going back, okay, so we had the direction of the graph, okay, to be opening upward. Axis of symmetry, we have x is equal to negative 4. The vertex we have at negative 4, negative 4. Okay, so it's going to open up, axis of symmetry. Again, we have x is equal to negative 4. And for the vertex, again, we have negative 4, negative 4. And for the x-intercepts, again, so we have negative 6, 0, and negative 2, 0 if I use coordinates. And for the y-intercept, okay, so the y-intercept, okay, so that is going to be at 0, 12. Okay, and if I were to identify at least 5 points, okay, so just kind of doing a quick sketch here. And on the y-axis, I'm just going to scale this at 2. Okay, so we have with key points here. Okay, so you have, again, the vertex, we have it -4, -4. And again, we have with the intercepts, okay, so we have -6, 0 and -2, 0. Again, we have with the y-intercept, okay, so we have it 0, 12. Okay, so we've got 4 points identified. Okay, and as for the graph of the function, okay, so you have a parabola that's going to be opening upward, and just throwing in the axis of symmetry. And that will serve a key purpose here. Again, that's just to keep everything in symmetry, thus proportion. Okay, so you have axis of symmetry, so you have x equal to -4. Now we have with the x-intercepts, notice that we have -2, 0. It's going to be 2 spaces to the right of the axis of symmetry. And -6, 0 is going to be 2 spaces to the left. And if I were to go up the axis of symmetry and have it level with the y-intercept, okay, so like right here, if I go up level, I would have like -4, -12. Not part of the graph, but just kind of give you a little bit of a visual. You've got -4, -12. And 0, 12 would be 4 spaces to the right. And to have it like a 5th point included, if I go 4 spaces to the left, and we have our 5th point, okay, so that is going to go, so you got 4 spaces to the right. If I go 4 spaces to the left, and still level with y is equal to 12, and we have 4 spaces to the left of -4, -12 is going to be -8, -12. So you got -8, -12. And in terms of graphing, again, we have a parabola that's going to be opening upward. Again, this is representing what we have for f of x is equal to the square of x plus 4 minus 4. And so these 5 points are among infinitely many other combinations of x and y values such that y is equal to the square of x plus 4 minus 4. Okay, now again, there's going to be alternating between the vertex and the standard forms of quadratic functions. And let me give you just kind of a quick case here. Okay, say if you have like converting between standard and vertex forms. Okay, again, just restate. Okay, so you have with the standard form, okay, we have y is equal to f of x is equal to ax squared plus bx plus c. And of course, for this to be a second degree function, okay, the leading coefficient a cannot be equal to 0. Again, so we have with the vertex form, okay, so you have y is equal to f of x is equal to a times the square of x minus h followed by k. And again, for there to be a square term, okay, we cannot have a to be equal to 0 either. And let's say that in terms of converting. Okay. So I have a function. I'll give you like a trinomial that technically is factorable. So you have convert y is equal to f of x is equal to x squared plus 6x plus 8 to its vertex form and then determine the vertex. Okay, so just for what we have starting out, okay, so we got f of x is equal to x squared plus 6x plus 8. Okay, so this is the standard form. Okay. Now in terms of transitioning over to the vertex form, what I'm going to do first, okay, is I'm going to separate the variable terms apart from the constant 8. So I'm going to put x squared plus 6x in parentheses. And what I want to do here is that with x squared plus 6x, I want to add in a constant. Okay, that's going to form a squared trinomial. And again, a squared trinomial is going to be a trinomial that factors out into the same binomial expression. Okay, like here for x squared plus 6x plus 8, it's a factorable trinomial, but it is not a squared trinomial. Like x squared plus 6x plus 8, that would factor to x plus 4 times x plus 2. So those are not the same binomial expressions. And what I'm going to do here, I'm going to perform what's going to be regarded as what they call completing the square. And for what this is going to be referring to, okay, so you have what's inside parentheses. Okay, so you have x squared plus 6x, and you want the first term inside, like with x as the independent variable, you want just x squared, nothing like 3x squared or negative 2x squared. You want only 1x squared to be at the front inside the parentheses. Now for completing the square, if the first term is just x squared or y squared, you're going to look at the first order variable term, okay? And in this case, we have it 6x. Now, for completing the square, you're going to take what is the number that is next to x, even if it's a decimal or a fraction. And what you're going to do with that number that is next to x, you're going to take half of this and square. Okay, so like half of 6 is going to be 3. And 3 squared is equal to 9. And what I'm going to do here, okay, is that in the completion of the square, okay, so what I'm going to do with the 9, first of all, I'm going to complete the square by adding 9. But to keep everything in balance, okay, getting it back to the form or the equivalent of x squared plus 6x plus 8, okay, if I just add 9 and do nothing else, I make this into something entirely different, which would be x squared plus 6x plus 17. So with the excess that is formed, what I add at the front, I'm going to take away at the back, because I'm back to the level of x squared plus 6x plus 8 with the 9's conceptually canceling each other out. But I'm going to keep these items here. And for f of x, I have equal to x squared plus 6x plus 9. And then for 8 minus 9, okay, so that is going to be negative 1. Now with x squared plus 6x plus 9, okay, so this is going to be a square trinomial. And so x squared plus 6x plus 9. Okay, this is going to be the square of a particular binomial. Okay, so from x squared I have x. And in terms of how I arrive at 6x and 9, okay, I look at how I got 9 in the first place. And that was taking the square of the constant value 3. Okay, so in this particular case, right, so whatever I square out to get to the constant to complete the square, that particular item that was squared, this will reappear in the vertex form. In this case, I'm going to have x plus 3 squared minus 1. Okay, and so I'm going to have f of x is equal to the square of x plus 3 minus 1. And for this outcome, okay, that is going to be the vertex form. And in terms of the vertex itself, see how this sizes up with respect to the general layout of what I have for the vertex form. Okay. So just looking at what we have here. Okay, so we have that a is equal to 1. And from x plus 3, if x plus 3 is 0, I have that x is equal to negative 3. So you have x is equal to h is equal to negative 3. And with the value of k, okay, we have subtraction to follow, so we have k is equal to negative 1. And so it's going to follow that with the vertex. Now the vertex hk is going to be negative 3, negative 1. Okay, so for this function, okay, so we converted, okay, from its standard form to what we have with the vertex form. And now, I'm just going to mention, I'll give you just a little bit of a quick case here. So we have f of x is equal to x squared minus 8x minus 20. Okay, so this would be a case of a standard form. And if I get to the vertex form, again, so I'm going to separate the variable terms apart from the constant. All right, so I have x squared minus 8x minus 20. So I had in the parentheses, I have the leading term to be x squared. Now, in the crossover to what's going to be referred to as complete the square. So we use CTS, shorthand for complete the square, not the Cadillac model. CTS, complete the square. So again, whatever's next to the first order variable, I'm going to take half of that and square. So negative 8 halves is negative 4. And negative 4 squared is equal to 16. So we have f of x is equal to the quantity. So you have x squared minus 8x, and again, completing the square results in a positive 16. So we'll add 16 at the front. And to keep everything in balance with x squared minus 8x minus 20, so you got 16 minus 20 is negative 4, but to have this to descend back to negative 20, again, I'm going to take the subtraction of 16 on the back side here. And so we have f of x is equal to x squared minus 8x plus 16, and negative 20 minus 16. Negative 20 and negative 16 amount to negative 36. And so we have x squared minus 8x plus 16. So I'm going to have a square trinomial. And again, so x squared is going to be the square of x. Now, in terms of the minus 8x plus 16, again, how I got to 16 in the first place was squaring out negative 4. And this is going to resurface in the vertex form. So we're going to have f of x is equal to the square of x minus 4 minus 36 so this is going to result as the vertex form. And for what we're going to have, at least in the case of the vertex itself. Okay, so your a is going to be at 1. If you think of x minus 4, setting that equal to 0, you have that x is equal to h is equal to 4. Yeah, so if x minus 4 is 0, x is equal to 4. And that's going to be our h value, and then your k value is going to be the subtraction of 36. for which we have, again, minus 36 for k, so that is going to be the resulting vertex.